All of mathematics arises out of real life, even pure mathematics, and the most fundamental real object is the space we live in. So, it's appropriate to study space before we study anything else, and that's why in M203 we'll be concentrating on the mathematics of space. And we start off in this program by considering some basic ideas of space. Ideas so basic, in fact, that we all take them for granted.
So, coming down to Earth for a minute, what are these ideas of space that we all take for granted? Well, space is just all the places where an object can exist and be moved about in. For an example, let's take an object we're all familiar with. If a bus drives out of the depot in the morning, and if in the afternoon it comes back like this, then we know it's travelled in ordinary space and ended up in a slightly different spot. But suppose it had driven off in the morning and had come back in the afternoon looking like this. Or like this. Well, we know those last two motions are impossible. Starting here and ending up like this, or like this, is just not allowed in ordinary space. And that's because we have in our mind an idea of which motions are allowed. They're the motions that don't alter an object in a fundamental way. Rigid body motions, which preserve distances. Well, the technical term for a function which preserves distance is an isometry. So, space is just all the places where an object can exist and be moved around in isometrically, where funny motions like this are not allowed. And that's the definition of space that we're going to take.
But hold on, Colin. There's a fundamental difficulty about that definition of space. It concerns the idea of distance. What do we mean by distance? How do we measure distances?
Well, one way to measure them is by carrying a ruler about.
Right, but carrying a ruler about gives you another problem. How do you know that the ruler stays the same size?
Well, that's easy. It stays the same size because you carry it about by rigid body motions, which preserve distances on the ruler.
But that's the problem. We've got a circular argument now. The way we break the circularity is by not attempting to define how we measure distances. We just say, well, we know what distance means intuitively. And we take rigid body motions to be those motions which we feel intuitively preserve distances. So to study space, to study geometry, all we have to work with are the motions which we feel preserve distances, the isometries. And that's the approach to geometry that we're going to adopt in M203. Well, what are these isometries? What are their most obvious properties?
Well, one thing we can see at once is that they form a transformation group. Remember, that means that they have to satisfy these three properties. Firstly, closure. They're closed under composition. That just means that if you take one isometry, followed by another one, then the combined result is itself an isometry. Distances are still preserved, in other words. So that's closure. Well, the second property is identity. Well, there's obviously an identity isometry. You just leave an object where it is. And thirdly, inverse. Given an isometry, then its inverse is still an isometry. So the isometries do form a transformation group. Well, to be very precise, a transformation group consists of functions from a set to itself. And the set we have in mind is the set of all points in space, not just the points on the double-decker bus. So, when we think of an isometry, we think of it as moving every possible object relative to some fixed frame of reference. So we're talking about the transformation group consisting of isometries of all points of space.
Well, I think this is a good point for me to step in and reiterate the point of view of this course. And the point I want to make is this. In M203, when we say we're studying ordinary space and distance, what we mean is we're studying this group. Now, you may have come across different geometries like the curved space-time of Einstein, and later on in the course, when we look at geometries like that, we'll define them by different groups of allowable motions. You see, different groups define different geometries, and that's the approach of M203. Well, let's get back to our ordinary Euclidean geometry, which is defined by this group, and we'll study it by using Euclidean concepts like straight lines, parallel lines, and so on.
Well, to make a start, we're going to define three special types of isometry using these concepts. You've seen these two already. Translation is just parallel motion. To translate, we just move all points an equal distance in the same direction. So we're using the idea of parallel lines. All points move an equal distance along parallel lines. Well, remember, these two objects are just here to show the effect of the translation on some of the points of space. You have to think of the translation as applying to all points of space. And that's true of all isometries, as I said before, including my second special isometry, rotations. For this, we need a line to specify the axis of rotation. So, that's my second special isometry. And by the way, I should point out that whenever we're talking about an isometry, it's only the beginning and the end positions that matter. The positions in between through which we actually did the motion aren't relevant. They're not part of the definition of the isometry. And that's true of my first type of isometry, translations, as well. Of course, it's natural to think of these two isometries as being realized by actual motions, but in fact, the third type of isometry can't be realized by an actual motion. Here's the image of a bus under an isometry of this last type. It's an isometric image because the distances between points of the bus are unchanged. But there is something different about the bus. In fact, it's a left-hand drive bus instead of the usual right-hand drive. Well, it's a reflection. Now, you can't get an object to its mirror image by an actual motion, but reflection is still an isometry because it leaves distances fixed. So, if we're trying to include all isometries, we have to consider reflections. And reflection is my third special isometry. Now, just as for other isometries, you have to think of reflection as applying to all points of space. And that includes points on the other side of the mirror. So what you have to think about is a double-sided mirror extending infinitely in all directions, so that a point on one side of the mirror has a mirror image on this side, and points on this side have mirror images on the other side. So, those are our three special types of isometry. And you may think that just defining those three types hasn't got us very far in our study of isometries. But in fact, the surprising thing is, those are the only types you really need to know about.
To be more specific, any isometry can be accomplished by a translation followed by a rotation. Or possibly it might have to be a translation followed by a rotation and followed by a reflection. Every isometry is either of this type or of this type. Well, that's an incredible result when you consider all the infinite variety of possible isometries. So let's make a start at proving that result.
Well, to do that, I'm going to take a tetrahedron, and I'm going to show that, given any isometry, you can reproduce its effect on the four vertices of the tetrahedron by a translation, followed by a rotation, and then possibly followed by a reflection. Once I've done it for the four vertices of the tetrahedron, In fact, I'll have done it for all the points of space, as you'll see in a minute. Well, we're going to concentrate on the 3 points A, B, C, first of all. And let's suppose the tetrahedron starts there, and the 3 points A, B, C end up here, A dash, B dash, C dash. Well, remember, it's an isometry, so the lengths of sides of this triangle are the same as the lengths of the sides of this triangle. So this triangle is the same size and shape as that one. And as a matter of fact, you can get this triangle to fit onto that one by a translation followed by a rotation without the reflection. Well, I'll do the translation bit. You first translate A to A dash.
Well, Colin, I think I ought to do some work for a change. Here I have a copy of the tetrahedron in its original position, and this is where it went to after Colin translated it. And now I have to show that I can get B and C to their images by a rotation. And here's a rotation about that axis, and that does it. And so what I've actually shown is I can get A, B, and C to their images by a translation followed by a rotation. Now, what about the vertex D? Well, after the translation and the rotation, it's ended up in this position. But remember, we only said what the isometry did to A, B, and C. Does that specify where it went to, where the fourth vertex D went to?
Well, the important thing to remember is that our original isometry preserves distances. So, whatever the image of D is, it must have the same distance from the images of A, B, and C that D had originally. And I've got 3 strings here, which are in fact exactly those distances. So, if I can find a position where all the 3 strings are tight, then I've got a possible position for the image of D. So that's one possible position, whereas that one there wouldn't be, because this string's now gone loose. In fact, there is another position if I take D right through to the mirror image position in this plane here. So, if this is the images of A, B, and C, then there's 2 possible images for D, one at the back there, and one at the front. And this one is the one that Alan's translation and rotation have got it to.
So either we've reproduced our isometry by translation and a rotation, or in the other position of the fourth vertex D prime, we'll have to follow through with a final reflection in the plane A prime, B prime, C prime. So given any isometry on the 4 vertices of a tetrahedron, we can get it by a translation, a rotation, and possibly a reflection at the end. But really, that's the result that we've been looking for, as long as we restrict ourselves to 4 points of space. Given any isometry, we can reproduce it by a translation followed by a rotation, or by translation, rotation, and reflection. Well, now that we've done that for the tetrahedron, for the 4 vertices of the tetrahedron, it actually follows for every point of space. Well, why is that? Suppose this is the final position that our isometry takes us to. Now, let's consider another point of space.
For example, this point. If we consider its distances from the 4 corners of the tetrahedron, A, B, C, and D, then that fixes it exactly. Well, that's simply because we've seen that if we consider its distances from A, B, and C, there's 2 positions, this one and a mirror image position. And then the 4th distance chooses which one of those. Now, if we look at the image of the 4 vertices A, B, C, and D, then there's a similar point here, which is also fixed by its distances. And since we're dealing with an isometry, it's got to take this point to that point. So, once we've reproduced the effect of the isometry on the 4 corners of the tetrahedron, we've automatically reproduced it on all points of space.
And now we have that result. Every isometry is a combination like this, or a combination like that. And that means our transformation group of isometries is much more tractable. We can more easily work out how the isometries combine. But it's still a very complicated group, so how are we going to study it? Well, a good way to study any group is by looking at its subgroups. And a rich source of subgroups for the isometry group comes from the idea of symmetry. We can study how symmetrical an object is by looking at what we call the symmetry group of an object. So we'll end the program by taking a glance at the idea of the symmetry group of an object.
Let's take this object, for example. It's a tetrahedron, but it's more symmetrical than the one we saw before. The base is an equilateral triangle, and the other three faces are isosceles triangles. I've got a copy of the base here, marked in exactly the same way, and if I put it on that, I'll regard that as the standard position for the tetrahedron. Now, supposing I apply a rotation through 2 pi by 3 about an axis passing through A. The tetrahedron ends up occupying exactly the same space. And when we have an isometry that puts the tetrahedron back occupying the same space, then it determines what we call a symmetry of the object. And if we take all those isometries, the ones that determine symmetries, then they form a subgroup of the isometry group, essentially the symmetry group of the object. Well, why is that? That's because if I take two such isometries and compose them, then the net result obviously puts the tetrahedron back occupying the same space. And if I invert one, then the same's true. So I get a subgroup, the symmetry group. And we're going to study that group. And in fact, all we're going to do is to count the number of elements it has. And in order to do that, I'm going to put this standard model back in its standard position. And I'm going to take a working copy. The working copy has the same lettering, except I've used small instead of capital letters, but I've stuck to a colour convention so you can see where the letters are. That's the rotation we've just seen, the one through 2 pi by 3, and there's another one through 4 pi by 3. And if I go another 2 pi by 3, then I end up back in the original position, with the identity symmetry, in fact. Well, that's 3 symmetries so far, 3 rearrangements of the base vertices, and here's a rearrangement of the base vertices where D is fixed and B and C have been interchanged. Can I realize that by an isometry? Is it a symmetry, in fact? Well, yes. All I have to do is reflect in the plane that bisects this face and passes through this edge. And obviously there's 2 more such symmetries given by the 2 other planes that pass through edges down from A.
And that's all. There are precisely 6 elements in the symmetry group corresponding to the 6 different rearrangements of the base vertices. And we get those 6 by 3 rotations about the axis through A and 3 reflections through planes through the edges from A. Well, what about a more symmetrical object, a regular tetrahedron where every face is in fact an equilateral triangle? Well, naturally we'll get the same 6 symmetries that we had before. And that corresponds to the 3 rotations about the A axis, and similarly we'll get the 3 reflections about planes through edges from A. But what about any other symmetries?
Well, we'd expect 24, because there are 6 rearrangements of the base vertices, and now there are 4 faces we can use instead of the base. Well, we found 6 symmetries already, and let's see if we can find the remaining 18. And let's work as before with a standard copy and a working copy with small letters instead of capital ones. So, for instance, if I put the working copy down in that position, then the thing occupies the same space, so it's a symmetry. Well, the first thing to do, obviously, is to look for symmetries of the type we've already found. Rotations about axes passing through vertices, and reflections in planes passing through edges. So, for example, that motion that I just did is such a rotation. It's a rotation about an axis passing through B. Well, now let's look for some reflections. Here's the reflection we saw before, with B and C interchanged. But here's a new position. This time, C and D are in the same places, but A and B have been interchanged. Well, you may not be able to read the lettering very easily, but if you remember the colour coding, then you can see that B's at the top where A was, and A's at the bottom where B was. Well, I can achieve this one if I reflect in the plane that passes through CD. This plane.
Well, that gives us 6 extra rotations and 3 extra reflections. Now, why is that? Well, for the rotations, we've got 3 new axes through B, C, and D, And about each axis, we have two non-trivial rotations of 2 pi by 3 and 4 pi by 3. So 2 times 3, 6 new rotations. And as far as the reflections are concerned, well, we have 3 new planes we can use through the base edges, and that's going to give us 3 new reflections. So altogether, we've got 9 new symmetries. We had 6 before, that makes 15 altogether. We expect 24, that means we have about 9 to go. Now, they're going to be of a different type from those. What sort of symmetries are they?
Well, here's a new symmetry. A's black and B's white, and they've been interchanged. And similarly, C and D have also been interchanged. Well, I can obviously get this by 2 reflections of the type we've already seen, but if I'm clever, I can do it by a single rotation. What I do is I choose the axis of rotation to pass through the midpoints of the edges AB and CD. So, put this in the standard position, and then rotate through a half turn, or pi, and I achieve exactly what I wanted.
And there are 3 of those because there are just 3 pairs of opposite edges. Well, 3 and 15, that makes 18, so there are just 6 to go. And the remaining 6 are quite intriguing.
Look at this symmetry. A is black and is where B was. B white is where C was. C is where D was, and D is where A was. In fact, the vertices have chased each other round in a circle. Well, a symmetry like this, where the vertices go round in a circle, we call a 4-cycle. And it's a fact that we can't achieve one of these by either a single rotation or a single reflection. Let me show you what happens when we try and achieve it by a rotation. Let's take the axis which passes through the midpoint of the edge DB and AC, and then rotate through a quarter turn. Well, I haven't achieved the symmetry, but I've done something. You see, A's on the left, as it should be, C's on the right, D's at the top, and B's at the bottom. But A and C are at the front instead of at the back, B and D are at the back instead of at the front. So what I need to do to finish it off is to compose it with a reflection in the plane perpendicular to this axis, which slices the tetrahedron in half. And then if I do that, A and C will go to the back, and B and D, which are at the back, will come to the front, and I'll get this end position. So that's the description of this symmetry. First rotate, then reflect, and we'll achieve this symmetry. So I've given you this symmetry as a combination of a rotation followed by a reflection, neither of themselves symmetries, but in fact this is really the simplest way of thinking of this symmetry.
And there are, in fact, 6 of that type of symmetry, because firstly, there are 3 different rotation axes like that, and you can rotate by both plus pi by 2 and minus pi by 2 for each one, giving 3 more possibilities. So that's our 24 symmetries.